Three-phase delta, the basics, voltage, current, and a few calculations. Delta systems differ significantly from Y-connected systems of either load or source, and that's because they form a delta symbol or a triangle as opposed to a Y shape. In delta, the phase and line voltages are always the same. And that's because of the nature of the connections. We can see that there's really no electrical difference between measuring here, or here, or here, or here. And because of that, line and phase are identical. There's a common number of voltages that we see for delta connected systems: 240, 480, and at times we do see 600. What defines a delta voltage will be that there is only one voltage provided, because there is only one possibility of voltage from a standard delta system. When we look at the phasor diagram for a delta system, we refer to the voltages not as A, B, and C, like in a Y system, but rather as A to B, B to C, and C to A. If we were to sketch these onto a phasor diagram, voltage AB would be at 0 degrees, voltage BC would be at 240 degrees, and voltage AC would be at 120 degrees. Now remember, voltages across the energy producing portions of a source or the voltage drop across a load will not change. The voltage remains the same across that particular item. And so the use of a phasor diagram in delta connected systems will be very, very limited. The other thing that is going to make delta a little bit easier is that we are only ever going to work with a balanced system within the confines of this course. Now, balanced means that the impedance and the power factor of either the load or the coils that are generating the power are identical in every way. If I have a balanced delta system, it then means that I can apply a very basic formula in order to define the difference between the phase and the line current. I line is always larger than the I phase in a delta system, and it's larger by root 3. And so that means that in a balanced system, if each of these were identical in current value, then my line current will be root 3 larger than any individual phase current, and each of my line currents will also be identical. Let's take a look at a connection that has not only my voltages, but also my currents. This is a load where we have resistors connected in delta. I have a phase current, a line voltage, and a line current. So unlike a Y system, we're only going to have one voltage type provided on the diagram. And unlike Y systems, we are going to have two different current values sketched onto the Y diagram. Now, what you'll notice is that I've sketched the phase current in phase with each one of the individual phase voltages that it's traveling through. So if we look at this one here, we've got EBC, and the current IBC is at the exact same angle. And that's because we have resistive loads. Now, some of you are looking at the pink, and we see we've got IA, IB, and IC, and for some reason, there is a difference of angle. Now, how we get this difference of angle, it is, well, lagging by 30 degrees, and we can see that IA is located 30 degrees below IAB. IB line current is 30 degrees below or behind EBC. And finally, IC is at 90 degrees, which is 30 degrees behind ECA. Now, the significance of this is very limited and marginal, and that's because the direction and the locations of each of these phasors really only has significance if we were to do calculations with an unbalanced system. There is a reason why the line current lags the phase current by 30 degrees, and that information is in a different video that you can take a look at, and it has to do with the adding of different types of phasors and vectors. But it's not a required portion of the course for us. So let's take a look at a few basic calculations when we're looking at a delta system. Remember, delta is only ever going to be balanced within the confines of this course, which means that we're not really going to be focusing on the phasor diagrams for these types of connections. So let's take a look at this connection. We've got a source and a load. They both happen to be delta. On the source, we have a phase voltage of 240 volts. Now we know that the line voltage is going to be identical to the phase voltage, and so what I can do is add in here the 240 volts. If the line voltage is 240, it means that the load phase voltage should also be 240. And so what we can do with this is then assign 240 volts to each of the three voltage items that we have listed on the far right-hand side. 240 volts, 240 volts, and 240 volts. Now we're going to look at the current, which is in the phase of each one of my loads. Now I've got A, which is located at the very top here. This one is C and B. The current that flows from A to B will be a basic Ohm's law calculation. And the Ohm's law calculation is going to take the voltage and divide it by the ohm value. So all we're doing is I phase is equal to, well, E phase divided by ohms. So we take our calculator, 240 divided by 10, and it gives me, well, you can barely even see it there, 24 amps. So 24 amps would be right here. Now, we said it's balanced, and we can see it's balanced because they're 10 ohms apiece, and they're all resistors. And so really, it's not necessary for me to do the calculation 3 times. That would be somewhat pointless. Instead, what we're going to do is simply take this number and copy it down an additional 2 times, because we understand that the current will be identical in each of these 3 phases. All right, so the last item we're going to calculate on this delta system will be the line current. And we know in a delta system, I line is equal to I phase times root 3. Now, because this is a balanced system, is why we are able to apply this formula to this particular current value. So I phase times root 3 means we're going to take our 24 amps and multiply it by root 3. 41.56 amps. Now that would be the current value that we see on this line conductor. Much larger than the phase value, root 3 larger. So 41.56 amps is going to be the exact same number that we get for each one of these individual line conductors. So for calculating in delta, The process is fairly straightforward. Let's do one more example. The next example we're going to do is, again, a delta source and a delta load. This time the delta load has 3 identical loads, but they're 8 ohms at a power factor of 0.6. Well, let's start with a voltage of 416 volts phase and look at what the voltage is going to be across each one of my individual loads. I have 3 of them and they're all the same. Well, if it's 416 phase, it means it's 416 line. And because of that, it should also be 416 phase across each one of my loads. So we can go ahead and assign 416 volts to each one of my individual phases. The next step is to determine the current in the phase, and don't let the fact that it is a dirty or a realistic inductor, as in XL and R. Rather, all we're calculating is the current. So if we're calculating the current, that means we continue to use our basic formula of I phase is equal to E phase, phase over the ohms, right? And so the phase voltage being 416, we're going to take that and divide it by 8. 52 ohms, or 52 amps rather. So 52 amps is what we have flowing through this portion of my delta system. Now I should add the 8 ohms. The assumption is that it's the Z, and I'm just going to clarify that to ensure that there's no confusion. That is the total Z of each of those 3 individual loads. All right, so we have 52 amps from A to B. We would have another 52 amps from B to C and 52 amps from C to A. That then brings us to the line conductors, and we know that the line current in a balanced delta system will always be √3 larger than the phase. And so we've got I line is equal to I phase times √3. This now means that if we take 52 amps and multiply by √3, we end up with 90 amps. So now we have 90 amps worth of line current, a √3 larger value than our phase. And of course, 90 amps is present on the remaining 3 line conductors.